In high school, you were told that electrons spin like tiny planets rotating on their axis, round and round, just like the Earth. And for a while, that explanation probably made sense. It helped you imagine something invisible. It gave you a way to make sense of magnetic fields, paired electrons, and atomic structure. But the picture you were given, it wasn't true, not completely. The idea that electrons are little spinning ball is simplification. And if you are being honest, it's wrong. Not because your teachers were trying to lie to you, but because the actual truth is weird. Weirder than most people are ready for in high school science. You see, electron spin isn't a spin at all. Not in the way we understand it in the real world. There is no tiny ball rotating. There is no axis, there is no surface, no classical motion. Electron spin is a quantum property, something that has no perfect analogy in everyday life. It's built into the very identity of electron, just like its charge or mass. So, why were you taught the wrong version? Because sometimes in science, we use simplified models to build a basic understanding, even if those models aren't entirely accurate. But today, you are ready for the real thing. What electron spin actually is, where it comes from, and why it matters more than you might think. Because once you understand this one strange abstract concept, you will start to see how the entire structure of matter depends on it. So, if electrons don't actually spin, then what is spin? Well, here's the truth. Spin is a fundamental quantum property of particles, like charge or mass. You can't break it down further. It's not caused by anything. It just is. For electrons, spin comes in two possible values, plus half and minus half. That's it, only two. Not a full range of speed or angles, just two options. We often call them spin up and spin down. But again, that's just a language. It's not describing any actual rotation. So why we use the word spin at all? Because this property behaves mathematically like an angular momentum. It acts as if the electron has some internal twist, something that gives it a tiny magnetic field, as though it were spinning. But, and this is key, there is no physical surface, no axis, no rotation happening in space. And this isn't just philosophical, we have tested it. You can't spin an electron faster or slower. You can't stop it from spinning. It always has spin, and it's always exactly minus or plus half. It's quantized, it's fixed in, built in. And here is something even stranger. If you try to measure an electron spin, you'll only ever get one of the two answers, plus half or minus half. There's no in between. Even if you change the angles of your measurement, it still collapses to one of those two values. This is not like anything in classical physics. This is the world of quantum mechanics, where particles have properties we can't directly visualize, but we can describe with stunning accuracy through math and experiment. So when we say electron spin, we're talking about a quantum label, a fundamental identity, not a literal spinning motion, an understanding that changes everything. A superposition, a blend of both spin up and spin down at the same time. But the moment you measure it, the superposition collapses and you get a definite answer, up or down. This isn't because your measurement was bad, it's because the electron genuinely doesn't have a different spin direction until it's measured. And the direction you measure matters. If you check spin along the vertical axis and get up, then check it along the horizontal axis, you would get a completely different result. Why? Because spin isn't just a value, it's a quantum property tied to orientation. Different directions mean different measurement outcomes. And that part of what makes spin so fundamentally quantum. Now you might wonder, what's the point of all this? Well, the simple fact that electrons can have spin up or spin down is what allows them to share atomic orbitals without breaking the rules of physics. It's also the reason materials can become magnetic, how MRI machines work, and even how quantum computers store information. But more than that in a moment. For now, just remember this. Spin up and spin down aren't about direction, they're about identity. They define how an electron can exist, interact, and ultimately build the structure of everything around us. A superposition, a blend of both spin up and spin down at the same time. But the moment you measure it, the superposition collapses and you get a definite answer, up or down. This isn't because your measurement was bad, it's because the electron genuinely doesn't have a different spin direction until it's measured. And the direction you measure matters. If you check spin along the vertical axis and get up, then check it along the horizontal axis, you would get a completely different result. Why? Because spin isn't just a value, it's a quantum property tied to orientation. Different directions mean different measurement outcomes. And that part of what makes spin so fundamentally quantum. Now you might wonder, what's the point of all this? Well, the simple fact that electrons can have spin up or spin down is what allows them to share atomic orbitals without breaking the rules of physics. It's also the reason materials can become magnetic, how MRI machines work, and even how quantum computers store information. But more than that in a moment. For now, just remember this. In 1922, two physicists, Otto Stern and Walter Gerlach, ran a little strange experiment. They took a beam of silver atom and passed it through a non-uniform magnetic field, hoping to learn something about the atom's internal magnetic properties. Now, if those atoms followed the rules of classical physics, the beam should have just spread out smoothly on the screen, like how a flashlight spreads light through fog. But that's not what happened. Instead, the beam split into two sharp lines. Not a blur, not a smear, just two distinct spots. This was shocking. It meant that whatever was inside those atoms, whatever was creating that magnetic response, it couldn't point in any direction it wanted. It had to be one of two options only. And what was causing that? Electron spin. Each silver atom had one unpaired electron, and that electron spin created a tiny magnetic moment, like a miniature magnetic point, pointing either up or down. The magnetic field in the experiment acted like a filter. It pushed spin up atoms one way and spin down atoms the other. And this was the first direct evidence that spin is real and that it's quantized. Not continuous, not classical, binary, quantum. The Stern-Gerlach experiment opened the door to an entirely new understanding of matter. One where particles don't just have properties. They only reveal those properties when we look for them. It's one of the most elegant demonstrations of how the quantum world works, in probabilities, superpositions, and sharp outcomes when measured. All from a cloud of silver atoms. And a clever setup that asks a simple question. Which way are you pointing? So now we understand what electron spin is, and how it's not a literal spin, but a quantum property with only two possible values, plus half and minus half. But here's the real question. Why does that matter? The answer is one of the most important ideas in all of physics, the Pauli's exclusion principle, proposed by Wolfgang Pauli in 1925. This principle says something simple, but incredibly powerful. No two electrons in an atom can have the same set of quantum numbers. That means if we have two electrons in the same orbital, same energy level, same shape, same orientation, they must have opposite spins. One spin up, one spin down. No exceptions. And that tiny difference is the reason atoms don't collapse. It's why electrons stack in layers instead of crowding into one spot. It's why the periodic table has its shape. It's why chemistry has rules. It's why matter has structure. Without electron spin and without exclusion principle, there would be no shells, no chemical bonds, no solids, no liquids, no gases. Just a pile of particles sitting on top of each other, doing nothing. Spin gives electrons their identity, and the exclusion principle gives matter its diversity. It tells us how atoms form, why they don't all behave the same, and why the world is stable, complex, and alive. So even though spin might seem abstract and invisible, its effects are everywhere, every material, every molecule, every breath you take, all shaped by the invisible logic of spin. So far, we have explored what spin is, how it behaves, and why it's essential to the structure of matter. But let's take it a step further. What does electron spin mean for the real world? Turns out, a lot. Let's start with the magnetism. The reason some materials like iron are magnetic comes down to electron spin. In most atoms, electrons pair up with opposite spins, cancelling each other out. But in magnetic materials, many electrons stay unpaired, and their spins align in the same direction. That alignment creates a net magnetic field. So when you stick a magnet to your fridge, that's billions of tiny electron spins working together. Next, we have the MRI machine, or magnetic resonance imaging. Relies directly on the spin of hydrogen nuclei, which are just protons. These protons also have spin, and in a strong magnetic field, they align and can be flipped using radio waves. The way they are returned to their original state gives doctors detailed images of your body's inside, without a single cut or drop of blood. That's spin saving lives. Now let's go even deeper into the world of quantum computing. In classical computers, bits are either 0 or 1. But in quantum computers, qubits can be in a superposition, both 0 and 1 at once. And one way to create a qubit is the spin of an electron. Its spin up and spin down states form the basis of quantum logic. Controlling that spin and maintaining it in a superposition is what makes quantum computing so powerful and so challenging. Finally, spin is also at the heart of quantum entanglement. Two particles can have their spins linked in such a way that measuring one instantly affects the other, no matter how far apart they are. That's not science fiction, it's been proven again and again. Spin is strange, spin is subtle, and spin is everywhere. The devices we use, the tools we depend on, and the theories that might one day change the world. So next time you hear the word spin, don't picture a tiny ball twirling in space. Picture a hidden property, fundamental, invisible, and powerful, shaping everything from atoms in your body to the future of technology. So now you know. Electron spin isn't a spin at all. It's not something you can picture or touch. But it's one of the deepest truths in modern physics. It explains why matter has structure, why atoms behave the way they do, why no two electrons can be exactly alike, and how a single quantum property can power machines, unlock images inside the body, and form the foundation of a brand new kind of computer. Spin reminds us that the universe doesn't always follow our intuition. Doesn't need to look like what we expect. It just needs to work beautifully, mysteriously, and consistently. And maybe that's the most fascinating part, that something we can't see or imagine directly can still shape everything we see and touch. So next time you hear the spin, don't dismiss it as a simple metaphor. Think of it as a window into the strange, elegant rules that govern the quantum world. Thanks for watching, and if this opened your eyes even a little, you have just taken one step deeper into the fabric of reality.